Hi guys, let's change gears now. We are going to talk about trusses. Please join me to this brief introduction to the topic.
Trusses are everywhere. They are used in bridges, antenna towers, cranes, even in parts of the International Space Station. And for good reason. They allow us to create strong structures while using materials in a very efficient and cost-effective way. So what exactly is a truss? It is essentially a rigid structure made up of a collection of straight members. But that's not a complete definition. There are two important assumptions we need to be able to make for a structure to be considered as a truss. First, we need to be able to assume that all of the joints in the structure can be represented by a pinned connection, meaning that members are free to rotate at the joints. The members of a truss are often rigidly connected using what is known as a gusset plate. But if the center lines of all the members at a joint intersect at the same point, like they do here, it's reasonable to assume that the joint behaves like a pinned connection. The second assumption we need to be able to make is that loads are only ever applied at the joints of the truss. We never have loads acting in the middle of a member, for example. Because all joints are pinned, the members cannot carry bending moments. They can only carry axial loads. This simplifies the analysis of a truss significantly. Each member has to be in equilibrium, so the forces acting at each end of a member must be equal and opposite. Each member is either in tension or in compression. These assumptions are what differentiate a truss from a frame. Unlike trusses, frames don't necessarily have pin joints, and so members can carry bending moments. A frame can also have loads applied directly to its members. The base shape of a truss is three members connected to form a triangle. If a load is applied, the angles of the triangle won't be able to change if the length of each of the members stays the same. This means that the triangle is a very stable shape which won't deform when loads are applied to it, and so it is a great base from which to build a larger structure. Joining four members together does not form a stable structure. The angles between members can change without any change in the length of the members, and so using a four-sided shape as the base for building a truss would be a terrible choice. An easy way to stabilize this configuration is to add a diagonal bracing member to split it into triangles. We can start with our triangle and build it out to form a structure. There are a lot of different ways to build a truss, but there are some particularly popular truss designs that you will see again and again, and so they are referred to by specific names. The one shown here is a Fink roof truss, but there are many more, as you can see here. Later on in this video, I'll cover how these different designs carry loads in different ways. The members of these trusses are all located in the same plane. These are called planar trusses, and we can analyze them as two-dimensional structures. Even seemingly three-dimensional structures can often be analyzed as planar trusses. Take a look at this bridge, for example. The loads are transmitted from the horizontal floor beams to the two vertical trusses on each side of the bridge. Each of these trusses only carries loads acting in its plane, and so we can analyze it as a two-dimensional structure. To be able to design or analyze a truss, we need to be able to determine the force in each of its members. This allows us to check that the member can carry the loads without failing, or gives us the information we need to select the best cross-section for each of the members. There are two main methods we can use to do this, the method of joints and the method of sections. Let's look at the method of joints first, using the Fink roof truss we saw earlier. The method is really simple. First, you draw a free body diagram, showing all of the external loads acting on the truss, and you use the three equilibrium equations to calculate the reaction forces. Then, you draw a free body diagram for every single joint, and work through them one by one to solve the unknown forces acting at each joint. You solve the unknown forces using the equilibrium equations. Since all of the joints are pinned connections, there are no moments, and so you only need to consider equilibrium of the horizontal and vertical forces. Remember that we are calculating the forces acting at each joint, not the forces in the member. If a member is in tension, the internal forces will be acting to make the member longer. For every action, there is an equal and opposite reaction, which means that a member in tension will be exerting a force on the joint which is acting away from the joint. For members in compression, the force will be acting towards the joint. Let's work through an example for a slightly simpler truss. First, let's draw the free body diagram and determine the reaction forces using our three equilibrium equations. Taking equilibrium of the horizontal forces, the horizontal force at joint A must be equal to 0, because it is the only force in the horizontal direction. Taking equilibrium of the vertical forces, the reaction forces at joints A and E must sum up to 20 kilonewtons. Both joints are located at the same distance from joint C, so taking equilibrium of the moments acting about joint C, we can calculate that they both equal 10 kilonewtons. Now let's determine the forces acting on each joint. Since we don't know yet which members are in tension and which are in compression, it's easiest to just assume that all of the members are in tension, and so we'll draw the internal forces as pointing away from each joint. If we end up with negative values for these forces, it just means that we guessed wrong, and the member is actually in compression. Now we can work through each of the joints, starting with joint A. Analyzing trusses involves a lot of resolving forces to different angles. So if you want to be good at it, you're going to need to remember your trigonometry. Here's a quick reminder. Back to our joint. All we have to do is apply the equilibrium equations to determine the unknown forces at joint A. Taking equilibrium of the vertical forces, the 10 kilonewton reaction force must balance the vertical component of the force FAB. And so we can calculate FAB as negative 10 divided by sine of the angle of 60 degrees. Taking equilibrium of the horizontal forces, we get that the force FAC must balance the horizontal component of the force, FAB, and so is equal to 5.8 kilonewtons. That's all of the forces acting on joint A calculated. The force in each member is constant, and so we now also know the forces acting on the joints at the other ends of these two members. We can repeat the process for joint B. We can start by considering equilibrium of the vertical forces, which allows us to calculate the force FBC. And then we can consider equilibrium of the horizontal forces to calculate FBD. We then need to work through all of the remaining joints, but we can save a bit of time by noticing that the truss and the applied loads have an axis of symmetry, and so the forces on the other side of the truss must be identical. That gives us all of the forces at the joints. We can show which members are in tension and which are in compression, like this.
Okay, that was nice. But let me stop our friend right there. He did a very nice introduction to the topic, and even he solved a complete structure in a fraction of a second. But let's slow down and take a look at some key points here before we get into what is called the method of joints to analyze trusses. A truss, as he said, is a structure made of elements that are connected at the joints that they don't hold any loads in the middle of the length. All the loads that are applied to these elements are applied in the ends of the elements. So all the elements of a truss are elements that fall into the category that we mentioned a couple of classes ago, that elements that only hold forces in 2 points. In these cases, the points are the ends of the element. Like here, this is an element of a truss that is holding forces at the ends. So an element like this is going to be an element that is subject to just two forces. So you can always add all these forces together into one final force, one final resultant here. And all these forces here, they will be added together into one resultant right here. So these two forces have to be collinear. They have to share the line of action like this. So either if it's in tension or if it is in compression, these elements will have an axial load. So this case or this case, there will be compression or this will be tension. So the load has to go through the axis of the element. Very important concept to make sure to understand that that's what makes a structure a truss, that all the elements are subject only to compression or tension. That's it. There is no flexion. If you put a load over here in the middle, that will cause bending like this. So that is not a truss element. He mentioned that very quickly, but I want to point out very carefully here. It's a very important concept. And now, he mentioned that in order to solve these problems, you make a free body diagram. So this will be like the free body diagram of the truss that he analyzes there. And then you use the equations of equilibrium to obtain the reactions, the external reactions. That will be these reactions here that I'm going to call here reaction at A in the y direction and reaction at A in the x direction. This will be the external load applied to the truss, kilonewtons, and this will be the reaction at point E. There is only vertical reaction because there is a roller there, so there is no horizontal reaction because the rollers just move. They don't oppose any. They don't create any opposition to the horizontal motion. So once you have the free body diagram of the structure and you calculate the external reactions, these ones, then you can start analyzing joint by joint in order to get the forces on the elements. So in this case, we want to find the forces in one, let's put it here, 1, 2, 3, 4, 5, 6, 7 elements. 7 elements. And we have 1, 2, and 3 reactions. So in total, in this case, we are going to find 10 unknowns. 10 unknowns. In the general sense, when you analyze a truss, you are going to analyze the joints as particles in equilibrium. So let's say, for example, joint A will be a particle with a force here, RAY, a force here, RAX, a force here, let's call it force in the element AB, and a force here, force in the element AC. So this joint here is considered a particle. So as a particle, we already studied that you can apply two equations of equilibrium. Summation of forces in the x direction is equal to 0, and summation of forces in the y direction has to be equal to 0. Since you have only two equations, in this joint, you can find two unknowns. In each joint, you can find two unknowns. You have two equations per joint. So if you have, in this case, 1, 2, 3, 4, 5 joints, 5 joints, and you can find two, or you can set up two equations per joint. So then you can establish 10 equations. So you count the number of joints in the structure and you multiply by 2, you can determine how many unknowns you can find. So that's what you see here. You have 10 equations, you have 10 unknowns, and that's how you can start to do your calculations, because if this equivalency between number of equations and number of unknowns doesn't hold, then you will be in trouble. If you have too many equations, those are equations of equilibrium. It means that you have to fulfill those conditions in order to guarantee equilibrium of the structure. If you have too many equations, you have more equations than unknowns, the structure is not stable. And on the other hand, if you have too many unknowns, you have more unknowns than equations, the structure is undetermined. So you probably won't be able to find all the unknowns because you don't have enough equations. But the structure is not unstable. On the contrary, it has too many elements to guarantee equilibrium. So let's do this problem using the method of the joints. He did it really quickly, but I want to do it kind of like a little bit slower, so and nobody falls behind. If you guys have seen this already, some of you probably have seen this before. It's a very easy method. You just have to be well organized, and work slowly. Make sure that you don't make a mistake. If you make a mistake in one joint, then that mistake propagates through all the other joints, and all your bars will be incorrect. So let's get started with this. We have the free body diagram of the whole structure here in order to calculate the reactions. So we then set up equilibrium equations. We can start here by using summation of forces in the x direction equals to 0. We have reaction AX, and there is no more forces, so equals to 0. So we found that reaction AX is equal to 0. We can take summation of moments in around point A equals to 0. So we have that we can say that positive in this direction. Remember we said when we talk about equilibrium of free bodies, you can take any convention of signs you want. So I have here the force of the moment produced by RE is in the counterclockwise, so it will be positive here. So it will be RE times 2D, the total distance from here to here is the lever R for that force with respect to point A. The other force, the 20 kilonewtons force, is at a distance D from point A. So, and that produces a moment in this direction, so it will be negative according to our convention. So this will be minus 20 times D, and no more forces in that direction. Therefore, that summation is equal to 0. So from here we got that 2RE D equals to 20D. So RE equals to 20 over 2 equals to 10. So RE is equal to 10 kilonewtons. Summation of forces in the y direction equals to 0. Let's say positive going up. So we have RAY positive, 20 negative minus 20 kilonewtons going down, plus RE going up 10 kilonewtons equals to 0. Therefore, RAY equals to 20 minus 10 10 kilonewtons. So we have here also 10 kilonewtons. So we have solved for the external reactions. So we can now go for the actual method of joints. We sweep joints all the way from left to right on this structure. So let me reduce the size of this a little. Let me put some labels here. This is A, B, C, D, E. Remember, each joint provides only two equations, so we can only go for joints that have two unknowns. If a joint has more than two unknowns, you have to move to a different one before you can tackle that one. So here we can start by analyzing joint A. You have to draw a free body diagram of each joint. So here we have joint A. The free body diagram of joint A will be like this. The joint is just a dot, and then the forces acting on the joint are AY, RAY, which is equal to 10 kilonewtons. The force Rx is 0, so we don't even draw it. And then the force coming from the element AC, we will call it FAC. And the force coming from the element AB, force AB. All the angles are 60 degrees, so we can put that in here, 60 degrees. And now the recommendation is to, as the guy said in the video also, the recommendation is to assume that the forces are all in tension. We don't know if some of them are going to be in compression. It doesn't matter. You assume all of them in tension. That's why I am putting this going that way and this one going that way. They are like pulling away from the joint, tension. Why tension? Because it's customary to use the sign convention that tension is positive and compression is negative. So when you assume all the forces in tension, all of them positive, so when you finish your calculations, you will find some of the forces being positive and some of the forces on the elements being negative. Those that you find that are negative means that your assumption was not correct. So instead of being tension, they are compression. And then since they are negative, that follows the convention of signs that is customary. You find the negative forces are compression, so that's the best way to write it. A negative means compression, and it means that the assumption that you did was wrong. Okay, now that you have the free body diagram of the joint, which is you have to do it, it's compulsory. Then you set up the equilibrium equations. Here we can do summation of forces. I will do summation of forces in the y direction first, because in the y direction I don't have components from the unknown FAC. So that allows me to solve for FAB directly in one equation. So I will do FAB sine of 60 plus FRAY, which is 10 kilonewtons, and no more forces in the y direction, equals to 0. So from here we can go directly FAB equals to minus 10 divided by sine 60 equals minus 11.5 kilonewtons. So we got a minus. A minus sign here means that this element is in compression. You don't have to look at, you don't have to even look at your free body diagram. You see a minus sign, you know automatically that is compression. Now summation of forces in the x direction equals to 0. So you do FAB cosine of 60 plus FAC equals to 0. Now you replace the value that you just found for FAB as minus 11.5 kilonewtons cosine 60 equals to minus FAC. So it goes positive, positive, FAC equals to 11.5 cosine 60, cosine 60, 5.77. 5.77 kilonewtons. You got positive, so this one is tension. Tension. So we could put those results here on the big diagram. AB compression minus 11.5 minus 11.5 and AC tension 577 tension. Let's put it in blue. And now you can go to the next joint. Next joint could be, it cannot be joint C, because in joint C you have 1, 2, and 3 unknowns. So we can go to joint B, because in joint B we have 1 and 2 unknowns. So we can solve joint B. Joint B. Absolutely important here. Main priority, you have to draw a free body diagram of each joint. Free body diagram of joint B. The free body diagram is just a dot. A dot. So we just have to put the forces on that dot. So we have force AB is compression. It means it's pushing the joint. It's compression. So it's pushing the joint. It comes here, pushing with a force of 11.5. If you put it in the right direction, in the right sense, pushing into the joint, you don't need to put the sign. Then we have another force that we don't know, the force BD. Force BD. Since we don't know this force yet, then we assume that is tension. So going away from the joint. The other force BC that we don't know is this one coming down here. Since this is still an unknown, we assume it in tension. And we put the a convenient name, so this will be force BC. And all the angles are 60 degrees. All the angles are 60 degrees. 60 degrees here, then 30 degrees here, 30 degrees here. Now, summation of forces in the x direction and in the y direction. What would be more convenient? Usually it's more convenient if you can, it's more convenient to set up the equations, initially the equations that can give you the solution for one unknown at a time. In this case will be the summation of forces in the y direction, because only the force BC has component in the y direction. If you use summation of forces in the x direction, both unknowns BD and BC will have component in the x direction. So you have an equation that you cannot solve by itself. So it's more convenient if you set up first the equations that can be solved by itself. So in this case will be forces in the y direction. In this case will be, if we do positive going up, so we will have 11.5 cosine 30 minus FBC cosine 30 equals to 0. So FBC equals 11.5 positive. So this is a force of an element in tension. Now summation of forces in the x direction equals to 0. So we have 11.5. We're going to do positive going to the right. 11.5 cosine 60 plus FBC, that is, we just found it, 11.5 cosine 60 also, plus FBD equals to 0. So FBD comes to be minus 2 11.5 cosine 60. 2 times 11.5 times cosine 60. 11.5. Negative. So we know automatically that this is compression. So we have solved this joint B. Let's put those values here in the main drawing. A negative 11.5 in BD, 11.5 negative, 11.5 negative here, and 11.5 in BC positive. So let's put it in blue. 11.5 here, positive right there. So let's take a look. This structure is completely symmetrical because this force doesn't exist. So since this is completely symmetrical, we can finish with all the other values. 11.5, and remember AB is telling us that DE is also 11.5, and AC 577, that will be here also 577. And this will have been the end of the calculation for this truss. That's the final solution. All the reactions and the forces in all the elements. So summarizing, you first start by solving the reactions using the free body diagram of the whole structure, and then you start sweeping joint by joint, making a free body diagram of each joint. Very, very important. Without this diagram, you are doing nothing. You do the diagram, and then you set up the two equations. Recommendation is, if you can find an equation where you can solve one of the unknowns directly, that's the best way to go. Sometimes that's not possible. And then you set up the other equation. You will set up only two equations at each joint. So it's very simple. It's very simple. This is a very simple problem, also very symmetrical and very few elements. So it was we could solve it really quickly. Not a big deal. But any regular problem will have many more joints, so you will have to make many of these little diagrams that you have to go through very organizedly, so you don't lose track of what you're doing. But in essence, it's very simple. Each diagram is very simple. You put the dot, the forces, the angles, or you need some dimensions in order to find the angles, because it's everything based on sines and cosines, and that's it. It's best to define all the angles before you start so you don't get stuck in the middle calculating angles. Another thing is that you don't necessarily have to start by solving the external reactions before you start with the joints. Eventually, if you can find a joint that you can start to solve without calculating the external reactions, you can do it. At the end, you will be able to find everything. You might get stuck at some point in one joint that you cannot solve because it has more than two unknowns. So you eventually might need to calculate external reactions before you finish. But that's not always the case. Eventually, you might be able to solve all the forces in all the elements and all the reactions just by sweeping the joints from left to right or starting from any joint that you can find that has only two unknowns. That's the condition. You can analyze only joints that have two unknowns. Okay, so now we just have to go for another example, maybe a little more complicated than this one.